Hello everyone, and thank you for attending this virtual session. I'm going to talk about our work towards petabit per second optical links. Today in many communication systems, electrical interconnects are being used to connect different blocks in a multi-core or multi-chip system. However, the performance of such a system degrades mainly due to the large loss of long electrical interconnects, as well as limited bandwidth, especially at high data rates. So to implement high data rate or high speed transceivers, we need an alternative to address these challenges. In the optical domain, however, we have access to a large bandwidth at optical frequencies. Also, we can implement very low propagation loss optical interconnects or waveguides compared to their electrical counterparts. In addition, optical systems are immune to unwanted electromagnetic interferences. Therefore, optical interconnects are promising candidates that can be used to realize high-speed communication systems. This slide shows the top-level architecture of our proposed system for beyond 100 terabit per second communication links. The system consists of 10 transceiver modules. Each transceiver module has 128 channels, and each channel operates at 80 gigabit per second. Therefore, there are 10 different fibers that connect to these 10 different transceiver modules. And in total, we have 1,280 PAM4 channels. The energy efficiency of our proposed system is 100 femtojoules per bit. And if you look at the figure on the left, we can see the structure of transmitter and receiver. On the transmitter side, the laser is coupled into the chip to generate an optical frequency comb. In this case, we are using an optical frequency comb as our optical carrier with 200 gigahertz line spacing. These different tones of, or different lines of the optical frequency comb are demultiplexed into different channels, and each is modulated by the corresponding data, and they're combined and transmitted over a fiber to the receiver side, where it is demultiplexed and demodulated, and the data is received. Starting with the optical frequency comb, that, as I mentioned, is acting as the optical carrier. In this case, we are planning to use a dark Soliton frequency comb, mainly due to the ultra-low on-chip operation power of such systems, and also the high conversion efficiency of pump laser to comb lines. Essentially, a large portion of the pump laser power in this method can be transferred into the comb lines, so the system is has a high efficiency. On the left, we can see the spectrum of 3 different combs as a function of pump laser power. For example, the top figure shows a frequency comb where the pump laser power is set to 23 milliwatts. I mentioned that the optical frequency comb is generated using micro-ring resonators, and here we can see that an optical frequency comb with larger than 120 nanometer bandwidth, around 1550 nanometer, is generated with 280 gigahertz comb line spacing in this example. And if you zoom into one of these comb lines, the optical signal to noise ratio is better than 50 dB. To demonstrate modulation and demodulation using the implemented comb, we have used a 2 gigabit per second PAM4 modulation signal, which can be seen in black in the top curve, in the top figure here. The comb is modulated, and also on the receiver side, it is received, photodetected, and the corresponding eye diagram is shown in blue here, and the received error rate is about 10 to the negative 13. In such a system, we need multiple different photonic devices that should be implemented together with the electronics. So in this table, we can see some of the different photonic devices that we have implemented in a 90 nanometer electronic process, SOI process. We have grating couplers, waveguides, crossings, waveguide bins, multi-mode interferometers, photodiode, and modulators. Most of these components have been actually implemented and tested. For example, our implemented Y junction has an excess loss of about 0.2 dB, and the photodiode has a bandwidth of about 40 gigahertz. If you look at the electronic photonic blocks that are required, some of the key blocks are the electro-optic digital to analog converter, or DAC in this case, that is used in the transmitter module. We are using a ring modulator that has two PN sections, and then the input beta stream is connected to these two sections for modulation. And then we have a third section, which is a capacitive phase shifter to tune the response of the ring modulator. Because it's a capacitive tuning, it is ultra low power, and essentially it doesn't consume any static power. At the bottom, we have the microphotograph of the ring modulator, as well as the layer stack of the capacitive tuning mechanism. This method can achieve a bandwidth of more than 30 gigahertz. On the receiver side, the key component is the photodiode, which has a 0.9 ampere per watt responsivity and about 40 gigahertz bandwidth. The microphotograph of the photodiode can be seen here in this slide. And also we benefit from some techniques such as self-equalizing photodiode scheme to enhance the bandwidth even further beyond 40 gigahertz. In this system, we also benefit from photonic inverse design methodology too, to basically optimize the performance of some of the key components in our system. One example is the grating coupler shown in this slide. We have a grating coupler consisting of a silicon and polysilicon layer within a cladding of silicon dioxide. The response of this grating coupler has been optimized around the bandwidth or wavelength of operation, and the efficiency is about 80%, and 1 dB bandwidth of this grating coupler is about 20 nanometer. And one of the most important advantages of these designs is that they are semiconductor fabrication compatible, so they can be integrated or co-integrated with the rest of our system. Another example is dispersion engineering that can be used for ring resonator implementation, especially for comb generation. In this case, we can start with a waveguide with a certain dispersion curve or characteristic on the left, as it can be seen in this slide, and then by doing some optimizations, we can come up with a new structure whose dispersion curve follows our desired goal or curve. Therefore, we can use this technique to achieve a very flat optical comb response. Finally, this table summarizes some of the key characteristics or specifications of our system. Its aggregate data rate is higher than 100 terabit per second. Energy efficiency is better than 100 femtojoules per bit. The optical carrier is generated using micro-ring resonator-based combs with 200 gigahertz line spacing, and all of the electronic and photonic devices are co-integrated on a 90 nanometer CMOS SOI process. This work is supported by DARPA PIPES program, And with that, I would like to thank you very much for your attention.
Okay, hello everyone. I'm happy to take any questions if there are any. Okay, I don't see any questions. So if there's no question, we can end this talk. But feel free to reach out to us for any further questions. Thank you, everyone.